Welcome to qnawire.
So we will calculate the angular velocities, omega equaling 2 pi over t, the period. And so we can calculate the angular momentum of the sun. This would be equal to the moment of inertia of the sun multiplied by the angular velocity of the sun. This is equaling 2/5 times the mass of the sun, modeling it as a sphere, times the radius of the sun squared, and then multiplied by 2 pi times the period of the sun. And so we can actually solve this, and the angular momentum of the sun is equaling 2/5 times the mass of the sun, 1.99 times 10 to the 30th kilograms, multiplied by 6.96 times 10 to the 8th meters, quantity squared. We're going to multiply this by 2 pi divided by 25 days. Because it takes 25 days for the sun to rotate about its own axis. And then we're going to multiply this by 1 day for every 86,400 seconds. And we find that the angular momentum of the sun is equaling 1.1217 times 10 to the 30th, or rather 10 to the 42nd, my apologies, kilograms meters per second. And so we can then calculate the angular momentum of all of the planets. So we're going to be doing the exact same thing. However, we're going to be treating it as a point mass orbiting around the sun. And then we're going to do this for Jupiter, Saturn, Uranus, and Neptune. So we can say that first, we can say that the angular momentum of Jupiter would be equaling the mass of Jupiter. We'll just say mass sub j. Radius of Jupiter squared. And now this is not the radius of Jupiter itself, but the radius of Jupiter's orbit. Because if we're treating Jupiter as a point mass, we're not going to be taking the moment of inertia of Jupiter itself. Or rather, we're not taking the moment of Jupiter itself. We're taking the moment of inertia of Jupiter rotating about the sun. So we're going to have to say the radius, or not really the radius, but rather more appropriately the distance from the center of Jupiter to the center of the sun squared, and then multiplied by 2 pi over, again, following the same lines. This would be the period, not of Jupiter's rotation about the axis, but Jupiter's rotation, Jupiter's period about the sun. So when it makes a full revolution around the sun. And so this would be the period of Jupiter's orbit. And so we can say that this is going to be equaling 190 times 10 to the 25th kilograms, multiplied by 778 times 10 to the 9th meters. Again, this is obviously much larger than the radius of Jupiter, because this is, again, the distance between the center of Jupiter and the center of the sun. And then it takes 2 pi over 11.9 years. So it takes 11.9 years for Jupiter to create one revolution of the sun. And then we're going to multiply this by, for every 1 year, there are 3.156 times 10 to the 7th seconds in 1 year. And so the angular momentum of Jupiter would be 1.9240 times 10 to the 43rd kilograms meters per second. And so keep track of this number, keep track of this value, and then we're going to do it for Saturn, Uranus, and Neptune. So let's do the angular momentum of Saturn. This would be the mass of Saturn times the radius of Saturn's orbit squared multiplied by 2 pi times rather 2 pi divided by the period of Saturn's orbit. And so this would be equaling, you can just plug in the values. They're in the appendices, or they're all tabulated online. And this would be equaling 7.806 times 10 to the 42nd kilograms meters per second. Similarly, the angular momentum of Uranus equals the mass of Uranus times the distance between the center of Uranus and the sun squared, multiplied by 2 pi over the period of Uranus's orbit. And this is equaling 1.695 times 10 to the 42nd kilograms meters per second. And as you can see, this is a little bit less than Saturn, and that's most likely because the increased distance from the center of Uranus to the sun is not great enough in order to account for the much larger period of Uranus's orbit. That's probably why this is much less. And then the angular momentum of Neptune would be the mass of Neptune times the distance between the center of Neptune and the center of the sun, or we can say the radius of Neptune's orbit squared, multiplied by 2 pi over the period of Neptune's orbit. And this is going to equal 2.492 times 10 to the 42nd kilograms meters per second. And then what they want us to find is the angular momentum, we'll call it F, the fraction of the angular momentum of the total of all planets. And then this would be divided by the angular momentum of the planets plus the angular momentum of the sun. So essentially, the sun's own angular momentum contribute to the total angular momentum of our solar system. And so we could add, this would be 19.240 plus 7.806 plus 1.695 plus 2.492 times 10 to the 42nd. We'll lose the units because, of course, we're dividing by the same variable, so the units are going to cancel out anyways. And then we're going to divide this by, again, 19.240 plus 7.806 plus 1.695 plus 2.492, and then plus that of the sun, so we'll round 1.122 times 10 to the 42nd. And we see that this fraction, we'll put it here, this fraction is equaling 0.965. So essentially, the angular momentum of the planets account for much more than the angular momentum of the sun about its axis in relation to the total angular momentum of our solar system. So again, F is equaling 0.965. This would be our final answer. That is the end of the solution. Thank you for watching.